All right, straight on to problem two. This is sort of the old traditional Superman who was faster than a speeding bullet, more powerful than a locomotive, and able to leap tall buildings in a single bound. So what we've been given is a building with a certain height, and we say Superman wants to leap it. He has to get up to that height and get over it. He has got a certain mass, and so what is the impulse he needs to give himself when he leaps up from the ground? Pretty simple, right? So we've got here's Superman. There's his cape, and the building has a height of h. And of course, he starts on the ground. This is, as I said before, he's able to fly. He needs to get up and then over. So his velocity when he gets to the top. So we want to know, first of all, we want to know the velocity he has to leave the ground with, right? His velocity when he gets to the top here is 0. So what we're going to use here is, we know velocity here, we know how high he goes, and so we need an equation that relates initial velocity, final velocity, height traveled, and then the acceleration of Superman, which is, of course, negative g. Okay, so I'm going to define positive y this way, up from the ground. And we are going to use this equation here, which is g final squared is v initial squared plus 2 acceleration in y direction. Easy, easy. So final velocity, we're going to call this spot final here. So what we need to do is find, when he's at the top, his velocity is 0. 0 squared is v initial squared. So the velocity he has at the start of his jump plus 2 times, what's the acceleration here? Well, g is acceleration downwards. Gravity always acts downwards. And we define y is going up. So we're going to say the acceleration is negative g, and then delta y is h. He goes up a distance h from the ground. So what that gives us is that vi squared minus 2gh equals 0, which means vi squared equals square root of 2gh. So that's his initial velocity. Now, what we are asked is, what impulse does he need to get off the ground? So what impulse does he need to launch himself at that velocity? Well, impulse, if you'll recall, is change of momentum. So now we're sort of talking about a different situation here. It's like this is a two-part problem. We solved part 2 first, where he has just left the ground at his initial jumping velocity, and he's got to get up to the top there. So the part before that, which we're going to do now, is this part where we have he's sort of on the ground, and he's got 0 momentum there, of course. So he's got momentum 0 there because his velocity is 0, and then he leaves the ground, just as he leaves the ground with this velocity of vi. Okay? So, which equals square root of 2gh. So when he's right at this point, what's his momentum? Well, his momentum is mv, right? Or vi, which is the velocity he leaves the ground with. So Superman's velocity as he launches then is m squared root of 2gh. And so the impulse here is, the impulse needs to go from this initial 0 momentum situation to jumping up off the ground at this speed. So impulse is change of velocity, and that is final velocity. I'm going to call this p. Let's call this p initial. I don't know. Let's see. It doesn't matter. This is his final velocity. P is this p here, and then we subtract his initial momentum. I'm sorry. His final momentum is this p here, and we subtract his initial momentum, which is 0. So the impulse he needs is just that momentum he's going to start with, which is going to be this, m squared of 2gh. So for my numbers, let's plug them in. Let's see. Superman has a mass of 120 kilograms, and the building is 215 meters tall. So let me get out my handy-dandy power calculator here. So what did we say? 215. So let's see. 215 meters, 120 kilograms. 120 kilograms is like 260. No, wait a minute. 240 pounds more. 254. Something like, no, 260 pounds. Yeah, Superman's a heavy guy. All right, so 120 kilograms times square root of 9.81, and the height was 215 meters. So looks like his initial momentum should be 5511 kilogram meters per second. So let's see if that is in fact what it is. 5511. I'm wrong. So let's see. What did I do wrong? So square root of 2. Oh, you know what? I forgot my 2. It was let's check that. But yeah, square root of 2gh, and I just plumb left out my 2. So 2 times. It's always tricky little things like that that'll get you. So 7793 or 7794 actually. But that's really too many sig figs anyway. So let's try 7794. 7794. And there we go. So I got that one right. Okay, so let's see about part B, which is if it takes him 0.07 seconds to lift off from the ground, what average force does he exert on the ground? And this is actually a much longer time than he would actually have to be able to push off the ground at the speed, but we won't worry about that right now. So, relationship between impulse and force is impulse equals average force times time, or the time that passes. And so recall we said 0.07 seconds, but let's do it symbolically first. So we want to find the average force is going to equal the impulse over delta t, which then, you know, the impulse here we found is equals to momentum, which is just m squared root of 2gh. So, do this all together. So average force is going to be m squared 2gh all over delta t. So really it's just our previous answer divided by delta t. So let's see if I can take this answer divided by 0.07, and I got 111,340, so 111,300. All right, so let's see, 111,300, and there you go. Now, just to sort of give you a frame of reference, G is 9.8. That's almost 10. So I'll tell you what. I'll just take that force and divide it by 9.81. So this force here is the equivalent to the weight of this many kilograms of mass. So that is 11,000 kilograms worth of force. You know, if you want to convert that to something you're familiar with, you can just multiply by 2.2 and get an approximate number of pounds. This is 25,000 pounds worth of force, which is a hell of a lot. And so the point of this problem, I mean, that's you know, your typical car. I mean, 25,000 pounds is like 12.5 tons. Okay, your typical car is like 1 ton. An SUV, like a big SUV, might be like 2 tons or so. So you're talking about sort of a mass, a weight equivalent to I don't know, half a dozen SUVs, 10 cars, maybe a big tractor trailer, something like that. So the point is that Superman, you know, just with his 2 feet, jumping this fast and this hard would put a tremendous strain on the ground. It'd be like having the weight of, you know, a bunch of SUVs concentrated onto just like, you know, the area of the soles of his feet, and it would just destroy the pavement. I mean, you got to imagine how much money the city of Metropolis has to put into their urban renewal every year just from Superman leaving these massive shattered cracks in the ground just from jumping off like that. So there you go.